Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking about kinematics of an object which is undergoing uniform circular motion. So, you may note or recall that in moving about in 2 dimensions, your kinematics requires one set of equations for x and one set of equations for y. Thus, if I have something like a projectile motion, I have a y component for the height above the ground and an x component for the range that the object has moved. So if I have something that undergoes a motion like this, then my y component would tell me this right here. My x component would tell me this distance right here. Okay? Now consider an object which is moving about on a circle, or the nearest thing to a circle that I'm going to be able to draw with my setup. All right, the object starts off here and maybe moves over to a location here. According to an xy coordinate system, yx, I would need 2 sets of equations to describe this motion. One to describe what's happening with y. Here's my y final. Here's my y initial. And then another to describe what's happening with x. This would be my x initial. This would be my x final, which in this case is actually negative. Okay, so if I have like a uniformly accelerating thing of some sort, then frankly it wouldn't stay on the circle. The acceleration actually changes in circular motion because the direction changes. And so this set of equations becomes a bit of a mess if we're trying to do everything in terms of x and y. So what we want to do instead is note that this circle that the object is moving around in some sense could be like cut somewhere and then stretched out into a sort of line position wherein we have one location here and one location here, and the object moves from one location to the other. Now, it's not perfect to say that this is a line because obviously the object could revolve around the circle a couple times, and that would, for a straight line, strictly speaking, be akin to moving from here over to here and then suddenly reappearing over here and moving and suddenly reappearing over here and then stopping wherever it stops. Okay. But we can instead treat this motion as if it's a line by converting our coordinate system. So, second point for the recall, we have 2 possible 2D coordinate systems, well, 2 commonly used 2D coordinate systems. Specifically, we have x and y, and we have s and theta, Cartesian and polar. So let's again redraw this circle, or some close facsimile of it. And let's again consider this motion from one location on the circle to another location on the circle. Well, I could call this location right here x initial, y initial, or I could call it the initial radius, s, and the initial angular position, theta. And I could call this location over here my final s and my final angular position, theta final. But I also notice that if this circle is centered at the origin, then s initial and s final are equal. And so I really have only one changing coordinate. Only theta changes. Okay, we want to make use of that to describe uniform circular motion. And the way that we go about that is, first of all, we note that x is equal to s times the cosine of theta, and y is equal to s times the sine of theta. Okay, so we can convert from xy into s and theta. And in doing that, we're able to kind of unlock some tricks here. Essentially, what we want to do is maybe convert from, strictly speaking, x and y into just simply position on the circle. And position on the circle, you could call this position 0 for theta 0, and essentially move about the circle some distance. And the distance that we've passed through, the arc length, often also we use an s for arc length, but I'm going to have to use a d since I'm using s for radius here. D must be s times theta. So we're letting s represent the radius of the circle, d represent the arc length, and theta be in radians. Okay. Now what that lets us do is now we can convert from x's and y's over to distance traveled. So in that sense, we have only one equation. Distance traveled, assuming a constant acceleration, would look like 1/2 times the acceleration times the time squared, plus the initial speed times the time, plus the essentially initial position. Okay, so we could say like d initial, something like that, where the acceleration in question is along the, call it d direction. Okay, so this is if it's speeding up and down. Now I'm papering over a little bit of physics here because in order to undergo circular motion of this sort, the object actually has two components to acceleration. There's the acceleration that makes it speed up and slow down, which is actually called tangential acceleration. And there's a second acceleration which is causing it to turn to stay on the circle. That's what's called centripetal acceleration. So properly speaking, this is the tangential component, and this is the tangential component, or the d-word component. And a sub c we worry about in a future lecture. Okay, if this is true, and note that we have to assume that at is constant, and I use quotation marks around that because, again, the direction is changing according to xy, but it's constantly pointing along the tangent of the circle. So there's a sense in which it is constant. The magnitude certainly needs to be constant. All right. So if that's true, then we can also write something like v tangential is a tangential times time plus v initial tangential. Okay. And in turn, a tangential is just constant. And now we invoke a second trick, which is what would happen if we divided everything by an s. So we're going to divide everything by the radius. Can do that both up top and down below. Well, we established over here that d is s times theta. So d over s would represent theta. Now we're going to introduce two other new terms, v over s, which will represent omega. I'll put quotations around this. This is the lowercase omega. Along similar lines, we can divide the acceleration by the radius and get this term alpha. This is a lowercase alpha. And that gives us a new coordinate system in which, rather than having to do x's and y's or even this weird d coordinate, we can simply use theta, omega, and alpha. And so for this same motion, I would say that theta is 1/2 alpha times time squared plus initial omega times time plus theta initial. And I can say that omega as a function of time is alpha times time plus omega initial. And as a bonus, I can even say that 2 times alpha times change in theta is omega final squared minus omega initial squared. And these assume that alpha is constant. So assumes a constant alpha. And these terms are basically the angular kinematics quantities. So angular kinematics. And again, I can take this set of quantities that I've written out here. I'm just going to copy them, drag them over here so I don't have to rewrite all of them. Maybe. And these quantities have the same kind of equations as what I could write down in regular kinematics, where I have something like d is 1/2 a t squared plus v initial t plus d initial, and v is a times t plus v initial, and 2a times delta d is equal to v final squared minus v initial squared. So these are kind of like linear quantities. These are angular quantities. And for that reason, we can say that theta represents, or not only that theta represents angular position, but that omega represents angular speed or velocity. Let's put little vectors over them just to really make it complete. And alpha represents angular acceleration. And so all that remains to be done then to complete this new angular coordinate system is to note that we need a plus and a minus direction for it. And essentially, plus is counterclockwise, and generally speaking, counterclockwise is true for all of these. For this one specifically, it's counterclockwise from positive x-axis, and minus is clockwise. So if you have something moving clockwise or accelerating clockwise, it's a negative angular acceleration, a negative angular velocity. If it is counterclockwise, it's positive. Okay, and now we've got it. We've got a complete system that lets us describe motion about a circle without having to use two coordinate systems with x's and y's. Moreover, the two coordinate system with x's and y's doesn't even do an especially good job of describing this motion on a circle, for the simple reason that the acceleration itself is not constant when the angular acceleration is constant. So now we have a more coherent way of describing this motion for something simple like constant angular acceleration. And that's all that I'm going to cover in today's video. Hopefully you've learned something, or hopefully it's given you something to think about, and thanks for watching.